So today we are going to talk about the Deutsch Jozsa algorithm. This is a generalization of the Deutsch algorithm that we talked about last time. So recall that in the Deutsch algorithm, we had a function from f going from 0, 1 to 0, 1. And we had to find whether the function is constant or balanced using a minimum number of queries to this function f. Now, in the classical case, it requires a minimum of 2 queries to find this out. However, we saw that the Deutsch algorithm required only 1 query to a quantum oracle, which is a black box called U of f. Now, the Deutsch Jozsa algorithm is a generalization of this idea. And in this case, in the Deutsch Jozsa case, we have a function from 0, 1 to the power n to 0, 1. And we are given the promise is that the function is either constant, function is constant, which means that all the values either go to 0 or all the values go to 1, or balanced. And balance means half the values go to 0 and the other half go to 1. So this is the promise, and we have to use our black box function or use this oracle and come up with an output which is yes if function is constant, or a no if function is balanced, using the minimum number of queries to this oracle. Now, in the classical case, we know that we'll have to query one more than the half the number of inputs to find whether the function is constant or balanced. So classically, we'll require 2 to the power n minus 1 plus 1 queries. And this is if we do a deterministic algorithm. So in the Deutsch Jozsa quantum algorithm, which we'll show shortly, it requires only 1 query. So quantum algorithm, which is the Deutsch Jozsa algorithm, requires only 1 query. All right, so let's go ahead and find the details of this. So before we go into the details and draw the circuit of the Deutsch Jozsa algorithm, let's have certain facts with us. So fact number 1 is that if I have a Hadamard gate or a tensor product of Hadamard gate, right? This is H tensor H n times, and I act upon it on the all 0 qubit, then this creates a uniform superposition. This is 1 over 2 to the power n over 2 summation over x n. This is x, right? And this is just a generalization. If I have a single qubit, we know that h acting on 0 is equal to 0 plus 1 over square root of 2. But it's easy to show that if you have a tensor product of Hadamard gates, then that acting on the all 0 state gives a uniform superposition of all possible n qubit states. The second fact is that if I have, let's say, H tensor n acting on a general state, not necessarily the 0 state, then you still get a uniform superposition, but you get it with some negative signs, and the negative signs are determined in the following way. So z belonging to 0, 1 power n minus 1 to the x dot z, z. And where x dot z is this inner product, x1, z1 plus x2, z2 plus xn, zn. So these are the two facts that we need to know. And this is an exercise. Both of these are an exercise to show. Exercise. All right. With that in mind, now let's go to the Deutsch Jozsa circuit. So circuit for the Deutsch Jozsa. So let me just draw the circuit. We have this is the circuit for the Deutsch Jozsa. And the top set of qubits is actually not just single wire. So this symbol is, there are multiple wires over here. So this is n wires. So 0 tensor n is the input state here. The single wire on the bottom part, it's 0. This is Hadamard tensor n. This is our u of f, which is the query. X, y, x, y, x, or f of x. So this is our query function. This is another Hadamard tensor n, and this is finally our measurement. Okay, and let's analyze this circuit. So let's draw the time points where we will look at the state of this quantum circuit. This is psi 2. This is psi 3. All right, and so I claim that at the end over here, we will get a answer whether the function is constant or balanced. And then since the circuit is called only one time, we'll the number of queries to the oracle will be just one. So let's start with what psi 0 is. So psi 0 is just 0 tensor n tensor 0 minus 1 over square root of 2. Then we have our Hadamard gate application, and I will use the fact number 1 over here. So this fact. So Hadamard, when it's applied to 0 tensor n, so you get psi 1 is equal to 1 over 2 to the power n over 2, summation x belong to 0, 1 power n, x tensor 0 minus 1 over square root of 2. Then we apply the oracle u of f. And as before, recall that in our proposition, u of f acting on x tensor 0 minus 1 over square root of 2 was minus 1 to the f of x, x tensor 0 minus 1 over square root of 2. Right? That was our proposition that we did last time. So psi 2 will be, which is post the oracle, will be 1 over 2 to the n over 2, summation x belonging to 0, 1 power n, minus 1 to the f of x, x tensor 0 minus 1 over square root of 2. All right. Now, before we get to psi 3, we apply again the Hadamard tensor n. And there we use this second fact. So Hadamard tensor N applied to a state X is this summation uniform superposition, but with some minus signs. So let's do that. Now, over here, we already have a summation. So when we apply the Hadamard tensor N, we'll get a double sum. So we have psi 3 equal to 1 over 2 to the N over 2 summation over X. And then we'll have a summation over Z. 1 over 2 to the N over 2. And then I'll get minus 1 to the f of x, and then they'll get minus 1 to the x dot z. And then we'll get z, and then finally tensor 0 minus 1 over square root of 2. So this complicated state is there, but I can rewrite it to a little bit. So let me rewrite it in a nice way. So side 3, so I can combine these two to get 1 over 2 to the n. And then I will interchange these summations. They are a finite sum, so I can interchange them. So I can get z belonging to 0, 1 power n. And then I have this summation x belong to 0, 1 power n. And minus 1 to the x dot z plus f of x, z tensor 0 minus 1 over square root of 2. Right? Okay, so we have got this state and now we are going to measure it. But before we measure, let's look at the coefficient. So coefficient in this inner summation, we want to look at the coefficient of z equal to all zeros. So this 0, 0, 0, n times. Right? So if I want to look what is the coefficient, if I put z equal to 0, I'll get 0 over here. So it will be, what will be this coefficient? It will be, this is going to be 1 over 2 to the n. Summation over x belong to 0, 1 to the power n minus 1 to the f of x. This is going to be the coefficient of z, all zeros, right? Now, we have two cases, right? The function is constant or the function is balanced. So this is going to be equal to, if the function is constant, whether it's either 1, f of x is 1 or minus 1, regardless, you will either get all ones over here or all minus 1. So this is going to be plus or minus 1. Right? If the function is constant. On the other hand, if the function is balanced, which means half of these values are plus 1 and half are minus 1. Regardless, they will cancel each other. So this will be 0. Right? So when we measure, if we get the values all zeros, that means the function is constant. If I get any other value of z, right? If I get any other value of post measurement over here, right? Post measurement, if I get 0, 0, 0, 0, 0, that means the function is constant. If I get any other value, function is constant, function is balanced. Right? So this is the Deutsch algorithm. And note that we have just made one query to the oracle as opposed to 2 to the n minus 1 plus 1 queries for a deterministic classical algorithm. So that's the Deutsch Jozsa algorithm.